Mm. Yeah, hi. Good afternoon, everyone. So we are really excited to have Mr. Matt Irwin with us today. He'll be presenting his presentation titled Hanford Tank Waste Treatment Briefing. So Mr. Matt Irwin is currently assigned as the Deputy Assistant Manager for the Waste Treatment and Immobilization Plant to support commissioning and transitioning to operations of the low activity waste facility. He holds a bachelor's degree in nuclear engineering from Arizona State University and has been a member of ANS since the mid-80s. He began his career with Lawrence Livermore Laboratory, followed by work as a shift test engineer supporting the Navy nuclear fleet. He joined Hanford in 1994 and has worked across the site as a facility representative and manager in the Facility Representative Program, Safety and Health, and now at the Waste Treatment and Immobilization Plant. So with that, we welcome you, Mr. Irwin, here, and we thank you for taking out the time to come and meet all of us and give a seminar. And with this, I'll just hand it over to you.
All right, thank you very much. So good afternoon, everybody. I hope you're all doing well. We are in a very exciting time at the waste treatment plant, so I will apologize. I will try to avoid using acronyms to the degree I can, but I will say waste treatment plant, we call affectionately WTP. My title, what that really means is I'm the Department of Energy second in command at getting the low activity waste vitrification plant through commissioning and into operations so that we can actually start vitrifying Hanford tank waste. So I'm going to talk to you a little bit about that here. I'm going to start big picture, and this is really just our mission and vision, and that's to safely manage the waste in Hanford's underground tanks while delivering the waste treatment capability needed for waste immobilization and final disposition. This next chart, I apologize, it's busy, but I wanted to give you a really big picture background at Hanford when it comes to tank waste. And really, for this slide, it's down here in the lower right-hand corner. Hanford is a 586 square mile facility or site in southeastern Washington. Back in its heyday, it produced approximately 60% of the plutonium for the United States. That production of plutonium was performed with 9 nuclear reactors. The liquid waste, we used multiple processes to remove that plutonium. Those multiple processes created a variety of liquid wastes that were stored in underground storage tanks. Here along the bottom left-hand corner, it shows you the sizes all the way from 55,000 gallon single shell tanks all the way up to greater than 1 million double shell tanks. We have 149 single shell tanks, 28 double shell tanks. In the early 2000s, we went through the process of removing all of the liquids from the single shell tanks, and we are currently in the process of retrieving that waste. And up here in the upper right-hand corner, it talks about the fact that we've emptied 17 tanks, 17 of the 149. Most of those are nowhere near their capacity in single shell tanks, but our double shell tanks are very close to their capacity. The constituency of the waste is made up of supernate, which is radioactive water. Doesn't mean it's not high level waste, because it is, but it in general it's at the top of the tanks and has the lowest particulate. We have some tanks that have salt cake and some tanks that have sludge and high degrees of particulate. And this provides just the general contents of that material. So what I'm really focused on, so all this stuff to the left is really our history, and we're going to show a couple of graphics that give you a little bit of perspective on that from a geographical standpoint. But my focus is in the waste treatment and mobilization plant, very specifically the low activity waste facility. So that's what we're going to be focused on here today, and that's what we're going to talk about. And at the end, we're going to talk about the commissioning, because that's what we're doing right now. This next slide just shows an overhead view of what we call the Central Plateau at Hanford. It's about 20 square miles. In the foreground here is WTP. We're going to talk about that in more detail here in a minute. Right behind that is tank farms. These little highlighted pointers are the various tank farms. This is what's called 200 East, which is where the majority of our tank waste is stored. And then in the background is 200 West. 200 West has 3 double shell tanks. The rest are single shell. We do have a cross-site transfer line that's not currently commissioned. But in all cases, the single shell tanks have been their liquids removed, and all they have remaining at this point is the solids and then any in leakage that happens over time. So that's just to kind of give you a picture of the overall tank farms and the Hanford Central Plateau. The 200 East, 200 West, just as an FYI, they're separated by approximately 7 miles. This is an aerial view of the waste treatment plant. What we're going to be focused on is the low activity waste facility. We finished that construction and startup testing in 2021. We're currently in the commissioning phase, and I mentioned in the beginning, this is a very exciting phase. We're within I'll just say it this way, we're within days of actually heating up the first melter, and you'll get a little bit of context of what that means here in a few minutes. Balance of facilities are the facilities that provide the various utilities. That's plant cooling water, diesel, steam, chiller plant, glass formers. So all of the things we need from a utility standpoint to make the low activity waste facility work. The analytical laboratory does all of our analytical work to make sure that we're mixing the right recipe of glass formers with the tank waste, so that we can then put it in the melter, vitrify it, pour that glass into canisters, and allow it to solidify, and then ship it off to the double-lined integrated disposal facility. Effluent management facility here in the lower right-hand corner, that takes our secondary waste. So when we're going to talk a little bit about the off-gas system for law. The off-gas system has a pretty extensive treatment system to deal with things like mercury, NOx, and the other chemical constituents that come off of the cold cap of the melter. And there are secondary wastes, liquid wastes that are generated by operating that off gas. The EMF serves to use an evaporator to boil off the H2O, collect any of the what we call the bottoms. Those are the particulates and other materials that come out of the secondary liquid waste treatment cycle, and then feed those back into law to vitrify it. I won't be talking about the pre-treatment facility or the high-level waste facility. The second phase of WTP is to treat the high-level waste, which that's primarily the sludges and the salt cake and the heavier metal constituents of the waste. That'll be happening. We're working on finishing the design for this facility, then we'll finish construction and get into that, and then we'll feed back in the lessons learned from operating the law facility into operating the HLW facility. So that's a little bit farther down the road, but that is part of our overall big picture mission. All right, so we have something we call direct feed low activity waste that covers all of the facilities and aspects that help us make law glass. And so this is an overhead. This is what you were just looking at up close. This is the tank farms here in the upper part of the picture. And basically, this is just telling the flow of the waste. It goes from, I'm going to show you a couple of pictures, tank farms through what we call a tank side cesium removal. That takes out the higher source term radioactivity from that law, ships it over through EMF to the law facility where we make it into glass. The glass goes out by truck over to the integrated disposal facility, which is up here in the upper left-hand corner. And then those liquid effluents, they go to EMF. The condensate from the evaporator goes down to the liquid effluent retention facility, and then is treatment by the ETF facility, which is basically just a little bit more advanced water treatment facility. And then as I said, the bottoms and the particulates from EMF go back into law and are treated through the low activity waste melter. So we're going to talk a little bit more detail about these things as we move forward, but I did want to share a few pictures. So this is a close-up picture of the AP tank farm. So that's a double shell tank farm. You see this little outline. Those are all the various penetrations. The tank is 8 feet underground, and these are double lined transfer lines with shielding above them. Those provide the untreated waste over to this, which is the tank side cesium removal. It's made up of ion exchange columns. Those ion exchange columns take out the larger particulates and the cesium, return it back into AP107, which is our feed tank for law. This facility started up here earlier this year, and this just gives a summary. This is a close-up of the building that has the ion exchange columns in it. Our first campaign, they processed 198,000 gallons, taking out 116,000 curies of cesium. The goal here for TSCR is to have in excess of 1 million gallons staged to feed the low activity waste facility. So it's been operating here in 2022. We'll be going into our third campaign here at the end of the year. And they'll have that 1 million gallons well in advance of us finishing the commissioning string. So this just gives a little bit more detail on where we are with WTP. We finished construction and startup testing. Startup testing was testing the functional capability of the individual components. That would be like level detectors, pressure instruments, flow instruments, all of the various components that support law and the support facilities. We finished that in 2021, and then on October 31st, we did what was called the loss of offsite power test. The reason that test is important is because the melter, when we start out, we use the resistance heaters, they're called startup heaters, to get us up to the 2100 degrees Fahrenheit to make glass. But once we filled the melter nominally half full, and I'll show you some graphics of this here in a minute, then we put in joule heating. And joule heating is just using the glass as the conductor, and we just apply that voltage across the melter, and it keeps the glass molten. The problem is once you have a full melter, if you lose power for an extended period of time, somewhere between 15 and 24 hours, then that glass will harden. And once it's hardened, then you lose the joule heating effect, and it's impossible to recover the melter. So it's very important that we make sure that all of our processes and procedures are in place, that if we do have a loss of power, that the plant reacts appropriately. And that initial reaction is to burn off the cold cap and make sure the secondary treatment train functions adequately to provide an elevated release and to continue to filter those off gases during the 2 hours that the cold cap melts off. And then the secondary function is to make sure that we restore power and that we have adequate power to keep the melters molten during that offsite loss of offsite power. So we did that on October 31st. I got a few things that we had to go fix. They were all minor. Then we did water runs, which is basically running water throughout the plant to demonstrate that we can move water into the feed tanks, move from the feed tanks to the concentrate tanks. Our off-gas system that I talked about, and I'll show you a graphic here in a minute, making sure that the HVAC system could operate in the appropriate zones and that the off-gas treatment components worked as intended. We aren't testing them yet, challenging them yet. And the mechanical handling proficiency, there's a whole bunch of systems that move canisters and equipment around. So those cranes and lifting attachments all had to be demonstrated. We trained and qualified 4 shifts. They work in a 24/7 DuPont shift to maintain the plant. Right now the plant is still cold, and we're today finishing up the melter heat up prerequisites so that we can actually start that heat up process, which we'll go into more detail here in just a sec. This just gives you a few pictures. This is an external picture of EMF here earlier in 21. These are actually the tanks that the condensate is stored in before it's shipped down to EMF. You can see them here in the picture on the right. And then the evaporator is inside the building. Law is above this picture. This shows the inside of EMF and the floor coatings that go along with it, and just some of the high pressure steam lines that provide steam for the evaporator at EMF. They also support the other facilities to help support the overall process. This is an example here in the upper left of a mechanical handling load test. We have a couple of hot cells. That's where the containers go once they're full to get deconned, get the lid put on them. And then once they're certified clean, then they can go out to the truck. This shows another example of a mechanical handling device that actually lifts the container up so that it can get the lid put on it. These silos here behind this truck, those are our glass formers. And so we have a whole array of glass former recipe that gets added depending upon each batch. Batch is nominally 9,000 gallons that goes into the melter in stages, but they generate a recipe based upon that tank waste. The materials from these silos are using a pneumatic system are actually delivered over to a mixer hopper in the law facility and then loaded pneumatically into the melter itself. On top of the melter, and that's where these people are standing right now, there we have things inside the melter like level detectors and what we call bubblers. The bubblers are literally that. They just bubble a gas through the glass to keep it mixed so it's homogeneous. These consumable changeout boxes are by crane brought over. The individual bubblers, when they reach the end of their life, which is nominally about a 6-month duration, they're pulled up into this. It has a bottom to it so that you're able to close this off. It's taken over to an export bay and then taken out as waste, and then new ones are put in reverse order. The actual pouring of the glass happens down in the pour cave, which is adjacent to this pour tunnel. The empty containers come in via what's called the bogey. That's this yellow device here on the tracks. Gets lifted up by this container, and then the actual pour cave is here just behind the people that you see in the picture. And that has a carousel. So there's one filling container, one empty container, and one cooling container at any time while the facility is operating. This is just another picture of the finishing line with a container that's in its lifted position that it can be put down on this table so that they can do the decon and then install the lid. Okay, so the phase we're about to go into is melter heat up, and I'd actually like to share a video because it actually highlights it. But this graphic shows what the melter looks like. It's basically a 300-ton melter made up of refractory on the outside. To start it, we put these 18 startup heaters in. We start to heat it up to temperature. We have a bunch of jack bolts on the outside because those blocks have to be, they're going to expand as the heat goes into the system. And you have to make sure the jack bolts are all aligned so that we're not overly stressing the blocks or having them loose. And then we'll fill the glass. So I'd like to stop sharing here and share a video that actually walks through the process. All right, let's see if I can show. This is where my skills really get tested because I don't get to use Zoom often. All right, where did the video go? Okay, I apologize. Technical difficulty. We'll go to plan B. All right, so there's the animation. All right. Well, let's go with entire screen. Oh, won't let me. All right. Well, I apologize. I guess I'm not going to get to share with you the animation. We can go back and walk through the slides, though. That's unfortunate. All right. So basically, we put the startup heaters in. The goal is to heat to 2100 degrees. That'll be done in stages. At each stage, they check the jack bolt torque, and we make adjustments accordingly. Once we get up to nominally, it's about halfway. The joule heating actually occurs across the melter. When that occurs, once we establish joule heating, then we're going to continue to add frit. Frit is just glass, and oh, didn't want to go that far. And then what we do is we remove the first 3 startup heaters and we put bubblers in their place. And the bubblers here are represented here. You put 3 of them in, that'll help mix it while it's still low. Startup heaters will still be supplementing the joule heating. Once we get it up to both full temperature and full glass, then we remove the rest of the startup heaters, install all of the bubblers, and then we're at the position where we can actually start to go into the melter checkout. Melter checkout involves basically starting to demonstrate frit pours. So at this point, we're just using frit. It doesn't have any of the simulant that challenges the off-gas system. The melters, each melter has two port discharge chutes. So you've got a carousel with 3 containers. One of those lifts up. Basically, after initial heat up, we'll demonstrate that we can actually use the air lance to put glass in each of the containers through each of the discharge chutes. Once we do that, then we're at temperature. Then we'll start to put the downstream. So the film cooler cools the air right off of the melter, which is going to come out somewhere around 1,000 degrees Fahrenheit. The film cooler cools that. It goes through a submerged bed scrubber, which is also providing some additional cooling and a little bit of particulate removal. It goes through the wet electrostatic precipitator, which is going to ionize the gas and capture those ions. And then we go, that all happens in a process cell. Then we actually go through the preheater, which takes out any, well, not any, but most of the moisture in the off gas, through HEPA filters to take out the particulates, goes through the carbon bed, which is a 2-stage lead lag setup to remove mercury. And then it goes into the TCO and the caustic scrubber, where we use ammonia to deal with the NOx and other VOCs. Once it goes through the caustic scrubber, then it's through the fan and out the stack. So once we get the melter hot, then we will systematically bring each of these off-gas trains on and confirm that they can operate at temperature. All of our testing up to this point has been at ambient. So we'll validate that all of those can happen at temperature. And then we validate that we're actually ready to introduce simulants that will produce the same constituents as our tank waste when we're making vitrifying glass. So that means it'll introduce things like NOx, things like mercury. So we'll introduce that simulant after we do what we call a cold commissioning management assessment. That cold commissioning management assessment validates that we've got all the people, plant, and paper in place to manage and control those hazards that are going to be introduced by that new simulant. Then we'll run through that simulant, which will take a period of 3 to 6 months, and then we'll do an environmental performance demonstration test. That will actually challenge all of these off-gas components. So it will actually provide chemicals above what we expect during operation. That's a big part of our permit with the EPA and Department of Ecology here in the state of Washington. And then that EPDTA provides the provides the basis for our permit. Once we've done that, then we'll be at the tail end of our cold commissioning, and we'll be able to do hot commissioning. Now, this period I just talked about is going to extend over the next year, probably about 14 months. And it starts with this melter heat up, for which we are working the prerequisites, and we're within the next week or so of actually being able to start up the melter. This is really just to kind of go back and show the big picture day in the life of how a individual batch of tank waste would go through the DFLAW process. It starts here in the center at AP tank 106, and that, I'm sorry, my bad, starts in AP 107, goes through TISCR, and it gets staged in AP 106. Then 8,000 gallon batches go through. The EMF is simply just a low point. So that means if we were to lose pumps, it all drains to this single point, and then we can deal with it from there. But it just goes through EMF over to LAW. LAW is a 24/7 operation. Already mentioned, it's 2100 degrees Fahrenheit melters. It's 2 melters, each one with 2 pour spouts, 300-ton melters. And they nominally will put out 3.5 canisters per day. And this just highlights, right, the degree of complexity. We have 5,500 procedures that help support that. Once the containers have been lidded and deconned, they'll go on the ILAW waste transporters, and immobilized low activity waste transporters, and take it to the integrated disposal facility. Then the rest of this picture shows some of the other support entities, like the analytical lab, the effluent treatment facility. The number of shipments that we get both in glass formers and diesel fuel, because that's what our steam plant runs off of, diesel fuel, The 222S laboratory is operated by another contractor on site. They do all of our radioactive tank waste samples at AP107, AP106, and others. Then just normal water and sewer. We get lots of, you can expect, we get lots of water to help support cooling, our occupational med facility, patrol, electrical utilities, water utilities, emergency and medical transport, and information technology. So this is really just showing the big picture, how the various facilities all work to help support the low activity waste facility. All right, so I know I talk really fast, and I am sure there are some questions, but that gives you a really quick thumbnail of what we're doing at Hanford relative to the low activity waste facility to manage our low activity waste for the Hanford tank waste treatment mission. So at this point, I'd be happy to answer any questions or any additional discussion.
Thank you, Mr. Irwin. Oh, yeah, Dr. Russo, go ahead.
No, go ahead.
No, I was just gonna say the floor is open for questions. So,
Matt, what makes it an 8,000 gallon batch? What is it about it that defines the batch size?
That's just the way they designed the feed tank. So they designed both the feed tank and the concentrate tanks at an 8,000 gallon volume. So I wouldn't say it's arbitrary, because that allows us to operate for nominally a couple of days in between batches. But it could have been 5,000, it could have been 12,000. It's really just the size of the tanks that were chosen for feeding the melter.
So 8,000 gallons, let's say 8,000 gallons goes into the feed tank, and then you operate the facility until that tank is empty?
There's two trains. So we operate off of that feed tank while the other feed tank gets its batch. We sample it, we add the glass formers, and we prepare that in the concentrate tank for the next batch. So there's two trains going on. Yes, one is fed until it's empty, and then you switch to the other one and then fill that one.
So the rest of the process is continuous.
That is correct.
Okay, good.
Largely continuous. So like I said, there's two discharge pour nozzles for each melter. So obviously when you stop filling one container, there's going to be a slight delay while you then start filling. I mean, we're talking minutes, but and then when you fill that full canister, the carousel will rotate one spot, and you'll lift up the next container for when the container on the second pour spot's being filled. But yes, we're nominally filling containers continuously, but there's obviously some machinations in between each container.
Sure. Thank you.
Yeah, no problem.
I think I had like a related question. So I was wondering, like, what's the usual like hold up times? For example, like from what we understand in the process, as you were also mentioning, like the composition of the incoming simulants is changing, right? I mean, that stays a little dynamic. So the recipe also of the glass formers that are needed to immobilize that waste depends on the composition of the waste that's coming in. So for example, once they get mixed in, let's say, the melter feed preparation vessel or something, what are like the usual hold up times? Like it again goes back to, is the process like really continuous? Like it continuously keeps feeding melter, or it stops for like a day?
We would expect to be continuously feeding. We don't expect to change the recipe from batch to batch. We actually expect to make it change from from tank, from the container at tank farms. So that 1 million gallon tank will probably have the same recipe throughout emptying that tank. Now, but we have the processes, because we have to sample each batch. And if there is a peculiarity in a batch, we do have to validate the recipe per batch. So it is possible we will make tweaks, but we don't expect to have significant tweaks other than over the life of the plant. So after each 1 million gallons, which is nominally about a year, it could happen a little sooner than that, but we probably won't change the batches more than once a year. Now, granted, when we start, obviously we'll be fine tuning that recipe, validating that the actual glass and how much of the radioactive materials are captured in the glass are as expected. If we aren't getting that, then we'd have to make adjustments, right? And there is a certain amount of uncertainty when you run it. How close are we going to be to the model? So I fully expect the recipe will change early on, but once we get that dialed in, it'll probably stay for a year at a time nominally. Now, the low activity waste will have less variability. When we actually get to the high level waste facility, that one will have a much higher variability because of the various different solids and sludges that we have in the various tanks. And that glass former facility supports both facilities. And the technology and the approach is the same for LAW and HLW. In HLW, it'll change more often. And that's actually part of the benefit of the approach we're taking, which is we will validate our processes on the lower hazard waste such that when we get to the HLW waste, we'll have perfected the operation of the glass former, our analytical samples, and how that adjusts the recipe. So that's the thought process.
Mm-hmm. So is there usually like a sampling point after the glass formers are added, or that doesn't? Okay.
Yep. So that analytical lab is taking all of those samples on the front end, mm-hmm. and they're basing it on the samples that were taken at tank farms and provided to 222S. And then ours is focused on the analytical part of making sure we get the right levels of the constituents in the recipe. Whether that's, well, I'll use the easy ones, silica, excuse me, and then all the other ones are much smaller constituents. But that whole sampling for the analytical lab is that front end recipe to make sure that we've got it all before we feed the melter. And then when we're doing commissioning, we will validate the glass itself. Now, we don't intend to actually take glass samples unless they're just shards of what we call shards of opportunity. So if there are shards during cooling, then we'll go sample some of those, but we're not going to go drill into an actual vitrified ILAW container to try and get samples at that stage. We want to prove it during cold commissioning so that when we actually are introducing the radioactive waste, we have high confidence that the glass we're making is what was expected.
Mm-hmm. Okay. I think just like one more question. So I think somewhere you were mentioning a pneumatic way of like maybe transporting chemicals. Was that for just like solid, like glass former solids?
They're all solids.
So
they're all like, they're all the constituency of either powder and or silica, like sand.
Mm-hmm. So I think like one of my questions was, so initially, like we know that the tanks are like underground, right? So how do you get that like waste or sludge at the upper levels? Is that also, I don't think it's pneumatically, do you use water to flush it out?
Those, the individual tanks over in tank farms, they have what are called either mixer pumps. So they can put mixers in one of the penetrations on the outside and that can mix a tank. But the transfer happens from a transfer pump. It gets put in down in the center of the tank. It'll pump up its column and then it'll go over to a transfer pit. And then those yellow lines, actually, well, anyways, the yellow lines I showed above ground, those hose and hose transfer lines, mm-hmm. Those are coming off of the transfer pump. The transfer pump comes up to the top of the tank into a pit that's on top of the tank. That pit has connection points that then connect to the hose and hose transfer. They send it over to that Tisker unit, which look like a big Conex box, goes mm-hmm. through the ion exchange columns, and then it gets pumped back into the AP106, which is our feed tank at tank farm. So that's not the feed tank where we had glass formers. That's just the tank that staged the waste over at tank farms. But those are big, gosh, I can't remember their capacity. But they're big centrifugal pumps that are at the bottom. They basically go in on a column and they're pumping up the column with a centrifugal pump at the bottom.
Okay. Thank you. I see Dr. Grover maybe has a question.
Thank you so much for that really interesting presentation. I was just trying to picture what will happen as you're pouring the glass into the canisters, and just curious about thermal expansion or shrinkage and what's happening in terms of the volume of that glass.
So it's basically it's poured into the canister in phases. So they'll add a third. Then they'll go over to the other canister and it'll add a third. And during that time, it'll cool. I can't tell you the exact, I could look it up I can't tell you the exact amount of change in volume as it cools, but I do know the reason we do it in 1/3 stages is so that it can cool and it'll solidify in the same constituent as the bottom of the. It's just like, right, if we filled it to the top and then let it cool, you can get gaps, but we do it in phases so that it'll be uniform lifts. It allows it to cool, and then they shift back. Each canister nominally will take 8 hours to fill, and then once it's full, then it'll go into a cooling spot. In that pour cave is a whole bunch of cooling panels that allow it to cool over nominally a 8-hour period in there. Then it'll go out into the pour tunnel and pour cave tunnel, and that tunnel will take it down into an area where it'll decrease the ambient. So I can't tell you the exact expansion and contraction, but I do know that we fill it in phases so that we don't create any gaps or any irregular distribution within the container.
Thank you.
Are there any other questions?
I have a question. It's just one of curiosity. What's the fluid in the SPS that your pump, that the gas is going through?
It's water. Yeah, it's water.
Wow.
Basically water in a recirc, and it has baffles so that the off gas comes, as you would expect, comes out at the bottom, and it just bubbles up through the water. And it's primarily for cooling, but obviously particulates will fall out into the bottom of the SPS. And then it's got a recirc pump that keeps that water circulating, and it has level detection so that it adds water over time, because obviously the off gas is going to cause a good percentage of it to boil away over time, but it's all water.
Hi, Mr. Irwin. Thank you for your talk. I have a quick question, if that's okay.
Sure.
So what is like the rough timeline for like approaching the high level waste? Because it seems like most of what's been done is on the low activity waste, it seems like.
So high level waste has a consent decree to initiate hot commissioning in 2035. We're currently in the design phase. We expect to be done with design. As you can see in the pictures I showed, it's partially constructed. It got suspended due to some technical issues with the overall process. Those technical issues have been resolved, so we're back into design. We will then get into full construction here within the next 2 years. And all I can really tell you, because I can't tell you more than that, is that it'll be done in advance of the consent decree. Same thing for law, right? The consent decree for law is to start up in the 2025 timeframe. That's the agreement between Department of Energy and the state, and we will beat that by a significant margin unless there's something dramatic that happens in the next year, which is certainly possible, but my job is to make sure we anticipate those and address them. So I know that's not a great satisfying answer, but that's everything that I can tell you based on where we are today.
Thank you. And I have one more, like,
Yeah, no problem.
It's a little more, I guess, specific. But you mentioned how
Sure.
they insert the bubblers into the melter, I guess, to keep it, I guess, well mixed, I guess. How do you get
Yep.
the bubblers out so that it doesn't also get incorporated into the glass, I guess?
So
Or is it like
maybe
pros
it's
that
best.
stick?
I'll show you. So that consumable changeout box, let's see if we go. All right. Can you see the screen again?
Yes, sir.
All right. So the top of the melt. So let's start with this picture. So this is the top of a tank farm, and I'm sorry, I don't have a good picture of this, but the top of the melter looks similar, but it's in rectangular form, but it has these covers just like this on the top of the melter. There's 18 of them. Those covers come off, and that's where the starter peters go. Those are penetrations that go down into the melter. And when those starter peters come up, the bubblers go in their place. Oh, there it is. The picture I was going for. this cylinder right here, it's literally a metal cylinder with a hoist at the top of it. And then this thing at the bottom by the people's feet, that's called a gamma gate. So that gamma gate gets bolted onto the top of the melter, which is what they're standing on, by the way. They remove the plug, and it's like that those tank farms penetrations I was talking about. This gamma gate goes on. The gamma gate has a gate on it that when you put it on top of the melter, it's basically providing a closed connection to the melter, so that you're not having an open path down to the startup heater that then is inside the bubbler. Excuse me, inside the melter. And the same thing is true of a bubbler. So there's a gate at the bottom of this cylinder. That gate opens, the hoist comes down, it connects to the top of the bubbler. They have a little window on the side here where they can confirm that it actually connected to the bubbler. It pulls out the bubbler. So as you can imagine, the bubbler is going to be covered with molten glass. As it comes out, it's going to cool, and some amount of that glass is going to solidify on the outside of the bubbler. But you still have confinement between this cylinder and the inside, which is where the bubbler is. You pull it up to the top, then the gate at the bottom closes, the gamma gate closes, then you can remove, it's a couple of latches. You remove those latches, the crane picks this up, it takes it over, there's an export gate and an import gate. The export gate is really just a hole. They go put this bubbler above that hole and drop it in. Then they could take the CCB over, pick up the clean new bubbler, bring it over, hook it up to the same gamma gate, open the gates, drop it in. Then once they do that, they actually open this window to connect it, to make the connections for the air. And then they close this back off, take off the CCB. That old bubbler that's now used, once it's fully cooled, then they come and pick it up with a CCB, take it out into the, basically there's a truck lock over here just on the other side of this wall. They can take it, they actually take it, drop it down through the floor. It goes through a little tunnel where it can get lifted up on the import side, gets put in a box, and then, gosh, I don't remember how many, I think it's 6 bubblers per box. Once they get to 6, they close off that box, put it on a truck, and send it over to the burial grounds, and it's buried as waste. Does that help?
Yes, I think so. So the bubblers are, I guess, removed before the glass starts its cooling process, like the melter.
So the bubblers stay in the melter, which always stays molten. The canisters is where the glass then cools, and then it gets taken out of the pour cave and it goes to the finishing line where it gets a lid. So yeah, the bubblers always stay in that molten glass, except when they're spent. And when they're spent, and basically it's because of that, as you imagine, that 2100 degree environment is hazardous for pretty much all metal. The refractory, because of its ceramic design, it lasts nominally. So an overall melter is designed to last 5 years. There's a similar but smaller melter over at Savannah River. Their melters have lasted longer, and so we won't be surprised if these last more than 5 years. But the melter itself will last nominally 5 years. Those bubblers are going to last somewhere around 6 months. And when they cease to be able to perform their function to distribute the air at the bottom and mix the tank so that it stays, mix the melter so that it stays homogeneous, then the bubbler will come out and we'll put a new one in.
Okay, thank you.
No problem. Yeah, I apologize. I know this is a lot, and I realize it's hard to digest all of that, and it's easy for me because I'm living in the facility every day. So I do know it's a pretty steep learning curve, and I understand there's lots of other details that I didn't cover, but it was really trying to give you a big picture view of what we're doing and where we're at.
Are there any other questions? I don't see anything in the chat either. Okay, then.
Oops. Sorry, I meant to stop sharing.
No, thank you so much again, Mr. Irwin. I think to the contrary, like I would tell you, like looking at the pictures actually helped us in understanding and like just thinking more about the process itself. So that was very helpful. Thank you so much for taking out the time and coming and interact with all of us. It was really very beneficial and knowledge. I would say it was a very knowledge-inducing seminar. So thank you so much.
Right. Well, I'm glad it was beneficial. For me personally, right, we're in a very exciting period. I would love to get to the point where I could tell Stephen that, yep, law's running and we're going to be starting up HLW right around the corner. And we're going to get to that point. We're just not there yet. So, you know, hopefully a month from now, I could tell you that the melter's hot. And a couple months from now, I could tell you we're filling canisters with simulant. That's where I hope we'll be. And that is very exciting. I think anyone who's heard about Hanford and WTP knows this has been a very long journey. There have been lots of fits and starts, but I'm happy to be involved at this stage. I've been here in WTP for the last 4 years, and we're really putting the big push to actually get to the point where we're making glass. I think once we get over that hump, we will be able to start to accelerate, and that'll be a really good thing, both for our mission and for Department of Energy and the overall Department of Energy mission as well. So thanks for your time, and happy to ramble on and tell you everything from my perspective. And if you have other questions, you can obviously send them via email. More than happy to provide more specific questions. Certainly process-wise, I'm more than happy to do that. Policy-wise, that's not my expertise. So
that sounds good to us.
All right. Thank you very much.
Thank you so much again. Yeah.
Thank you.
Thank you,
Have a great
Mr.
day.
Irwin.
Thank you.